Well, hello there to anyone watching this video. This is Mrunal Kubde. My uni ID is U778172 and this is my submission for HPO for Phase 2 which I submitted to Josh on 28th of October 2023. For this particular project, I have no partner. This report was solely made by me and me alone. The scenarios and conditions taken for this particular projects were done by me. Well, in this project, I try to understand the working principle behind double pendulum. For this particular project, we have to go through and I had to go through and research the following topics as butterfly effect, chaos theories, fractals, Lorentz system, and three-body problem. Well, chaos theory tells us how change in the variable changes the whole system. This was further able this was made further able to comprehend by Sir Hamilton and Lorentz in their Lorentz system of weather prediction, which was done with the help of supercomputer. Cause why not use a supercomputer? Huh? Well, I don't have a supercomputer. I tried to understand the working model of double pendulum with the help of simple scenarios and simple conditions by taking different angles and different length for the pendulum. Here you can see my experimental setup where M1 is the bob 1 and M2 is the bob 2 for the particular experiment. We can only make approximation through this approach. There is no way we can predict the future trajectory of the chaotic system. We can only speculate that it may take this approach or it may not, based on various variables such as wind, humidity, friction between the ball bearings, and yeah, turbulence in the system. Now I will show you the animation of the of my project. But before that, I wanted to emphasize on the fact that Newton too tried to comprehend the working principle behind three-body problem, which he was not able to do. And well, it was because there is no way we can 100% predict the future of a three-body problem. The only way we can we can understand and predict the future of three-body problem is through numerical analysis of dt time step, which I have also used in this particular experiment in order to give the trajectory. This was done so with the help of tracker program, which I will show you in a bit. But before that, I want to show you the animation which I prepared in Mathematica and how cool it looks. Yep. So this is the animation program which I created in Mathematica, and look how cool it simulates the trajectory of double pendulum just by putting the angles. For case one, I wrote this code and I put alpha to be 180 degree and beta to be 270 degree. If I run this code, I will get the future trajectory of my double pendulum. As you can see from the simulation shows the working principle behind the double pendulum. And for case 2, I did the simulation again with with the help of mathematical program for 270 degree and 178.5 degree. If I run this code, it will give the simulation for the future of the double pendulum trajectory. And for case 3, I did it again for an angle of 271.1 degrees and 271.1 degree beta. Again, my code gave the future prediction of the model, but There are various factors which will affect our trajectory for double pendulum. This, for example, is what should happen if the if the environment was ideal. And by ideal I mean there is no air resistance, there is no turbulence, there is no drag, there is no friction, nothing. uh, this is what I mean by ideal scenarios. But the thing is, there is no such thing as ideal scenarios. We can try to make we can try to simulate, we can try to do our experiment in isolated environments, maybe try to reduce frictions by lubricating the ball bearings, but there is no way we can 100% get an ideal scenario. This was my observation, because when I tried to do this with the help of uh, 3D pendulum, which I designed in the makerspace, I got to the conclusion that there is no way we can predict the model. Uh, I'll show you now the code which I wrote for my double pendulum. This is a code which I wrote for my which I wrote for the analysis of double pendulum, in which I first defined the variables for positions for my two masses on the double pendulum, and I defined the kinetic energy and potential energy for the system, which was simplified. And then I calculate the Lagrangian for this particular experiment. Then the parameters were defined here. M1 is 0.99, which means like it was no, it was not 0.99, it was 0.099, and M2 was 0.099, because my ball bearings were almost 100 grams. Well, the sticker showed 100 grams, but I measured it with the help of weighing scale in the makerspace. It gave me a reading of 99 grams. So this is the 99 grams, and the G is the acceleration due to gravity in Canberra, which is almost equal to 9.792. L1 and L2 are the length of arms for my double pendulum, which when calculated with the help of vernier caliper came out to be 0.05 meters, which is 5 centimeter. Then I tried simulating the case 1 where alpha is 270.1 pi by 180 and beta is 178. Before this, in order to explain the trajectories and all, I'll show you my experimental setup and what I basically did in order to understand what the reality or what pendulum will do in the real scenarios. I'll first show you my video which I captured. Video. In this you can see that I 3D printed this double pendulum, and which was further clamped to the clamped to the table with the help of these two clamps, and in order to reduce the turbulence. For turbulence in the system, I use the ball bearings to reduce the friction in the system. Then I kept it. Then I kept the camera straight to my model in order to reduce the angle discrepancies, in order to reduce the uncertainty in the angle. Also, the angle was calculated with the help of tracer program, which I will show you in a bit. If I run this, you can see me setting up the angle and releasing the pendulum. Then I clipped out a 10-second video from this, from the moment the pendulum was released from the state of rest. This was then further studied with the help of Mathematica code and tracer program. I'm sorry, I was referring to tracker program as tracer. That's my bad. But onto our experiment. For case 1, we take alpha as 180 degree and beta as 270.1 degree, as we can see through our diagram here. This is calculated with the help of protractor function in tracker program, and if we run this simulation, we'll get an observation as follows. If we recheck this with the help of our graphs, we can see for mass 1, that is bob 1, this is the curve for x versus t, and this is for y versus t. If we plot a curve for bob 1 x versus y, we'll get this kind of curve. And when we check this curve and compare this curve with our ideal case scenario, we see that it is not as follows. If we now check the curve for bob 2, that is mass b, x versus time curve and y versus time curve is as follows. And if we analyze a curve for bob b, x versus y, we'll get this curve. We can see that this realistic curve, or as a real case curve, will follow the ideal case for some time and then diverge out and will go totally random mode, as compared to ideal case scenario where there is a predefined path which the pendulum will follow. And now I'll tell you what I did with the tracker program. I took a clip of 10 seconds and analyzed it, which was from 465 frame to 565 frame, and dt was 0.1 second. Yeah, so now I'll show you my observation for experiment number 2. For this particular case, you can see this was my setup, and now I'll insert the initial conditions in my code. Alpha to be 271.1 and beta to be 271.1. This was again calculated with the help of compass feature in tracker program, and this particular graph is the result of this initial conditions. Here we can see the trajectory, ideal case trajectory for the pendulum, double pendulum. Now if we compare this with what we got in the real scenario, we will this is the curve for mass 1, bob 1, x versus time, y versus time. And now I did the analysis for mass 1, x versus y, and this is what I got. uh, Maybe somewhat similar to what ideal case gives out, but we'll see. So this is the plot for bob 2, that is mass b, x versus time, and y versus time being in seconds. When I analyze this curve for x versus y, I got this plot, which is also somewhat similar to the ideal case. So we can say that this experiment did follow the ideal case scenario to an extent. Now on to the experiment, or last experiment, or my last experiment. For this we can see this is the setup, this is the experimental setup for my double pendulum, where I'll put the initial conditions in my code right now. 180, no, 270.1 and 178.5. Again, this was also calculated with the help of compass feature in tracker program, as you can see in this particular image. If I simulate this code, I'll get a trajectory of this. Now what we'll do is we'll compare this with our real life trajectory. So wait a second. Yeah, so this is the x versus time curve for bob 1 and y versus time curve for bob 1. When I analyze this for x versus y for bob 1, I got this particular graph, which again did follow the ideal case scenario to an extent, but not completely, because this is a real life output. This is the plot for bob 2, mass b, x versus time, y versus time. Again I analyze the curve further for x versus y, in which case I got this curve. We can clearly see that this does not follow the ideal case scenario, as every curve does not, because of various factors such as air resistance, friction, etc., etc. Now in conclusion to what I did for this particular experiment is, even though the theoretical and experimental results are not completely identical due to the many assumptions and factors discussed before, the pattern of the derived results are pretty close to the support of my previously stated conclusion that double pendulum is a chaotic model. We can not completely define its trajectory. We cannot predict the trajectory of double pendulum. Small changes in initial condition will give totally different results than that of the previous cases, even though the cases are somewhat similar to each other. Minute to minute details should be noted for this particular experiment, and while conducting, there are certain things that I overlooked for this particular experiment, which I'll show you right now. As we can see in this particular figure, this is not an ideal pendulum.
because we can see for an ideal pendulum the mass in the arm should be negligible, but for our case we can clearly see that it's quite heavy. Yeah, it's quite heavy. Also, the ball bearings used for the experiment were quite stiff. There was constant friction between the parts of the equipment. This led to changes in the trajectory and deviations from the ideal behavior. Thank you.